in front. It's both okay.
Which one's better?
Both. It doesn't matter.
Thick
You can also
belt.
put it here. That's also okay.
Okay.
And this one in the middle. There or here.
Here? Okay. Hi.
Yes.
Okay. So this only records the sound and my voice. It doesn't amplify, right?
Yes, it's for the recording.
Okay. Oui, Thierry. Ok. Il vient pas? Oh, hi. Yeah.
You want yours?
Yeah. I'd like to use it. So it should work now. Okay. And the laser pointer. Okay, thanks.
Okay.
Okay. Welcome.
Shall we start?
And first speaker of the morning is Nadi Bizi, and the title is the Lorentzian noncommutative standard model.
Thanks.
That's it.
Hello, everyone. So it's finally Lawrence Day, huh?
Yeah.
Yeah. So I have to tell you something first. The initial title and abstract of my talk might be a bit misleading because I said I would be talking about noncommutative differential forms and Lorentzian signature. Well, two things happened. First, the topic of noncommutative differential forms has been covered to death by Latham and Shane, so I won't be talking too much about it. I'll be applying it, but I won't be presenting it, okay? And the second thing that happened is that I have too many things to say on the signature of space-time, so we will focus on that, okay? All right, so this is some work I did with Christian Brouder, who's here, and Fabien Bénard, who could not join us, but I'm sure he will be watching the video of this talk once it is online, so salut Fabien. All right, let's get started. As we all know, noncommutative geometry enables us to have this very nice formulation of the standard model of particle physics, but it still has two issues. The first issue is that it's still a classical theory, okay? So it needs to be quantized. I won't talk about this. I will focus on the second issue, which is that most formulations of, the standard formulation of noncommutative standard model is Riemannian, and we want it to be Lorentzian, or pseudo-Riemannian if possible, okay? If it could work with all signatures, that would be nice. What happens when you switch from Riemannian signature to Lorentzian signature is that you need to replace your Hilbert spaces with indefinite scalar products on them. And these spaces will probably be Krein spaces, okay? This is the indefinite analog of a Hilbert space. Now, this has been suggested by many authors who work on noncommutative geometry. In fact, one of them, Van den Dungen, is here, and he will be talking this afternoon. And I have to say that his latest paper was very interesting. We drew some inspiration from it. Okay, now we know that we need to replace our Hilbert spaces with Krein spaces. What happens then? I mean, you have to ask yourself, how do the axioms of noncommutative geometry change? And today I'm going to tell you our answer to this question. Okay? So I'll be presenting Krein spaces. I'll try to tell you why they are necessary. Then I'm going to use them to construct indefinite spectral triples. I mean, our version of indefinite spectral triples. There are many versions now. And then I will go to the standard model. But first, to construct the spectral triple of the standard model, you need to build a tensor product of spectral triples, because the spectral triple of the standard model is a tensor product of two spectral triples, okay? So I'm going to show you a version of tensor products for spectral triples that is quite compatible with Krein spaces. We'll use that, we'll build the standard model, we'll get the fermionic action, which will confirm that the spectral triple kind of works. And then I will tell you how it is possible maybe to get a bosonic action. But I won't elaborate on that very much. We're still work in progress. And then I will conclude, okay? All right. Let's get started. First, why crime spaces? Okay, consider this. You have a manifold. You have some signature for your manifold, okay? You have a number of time dimensions, a number of space dimensions. You build your Dirac operator here. This is my convention for the Dirac operator. And then you want to build a fermionic action for your model, okay? And if you want your action to be real, you want your Dirac operator to be self-adjoint with respect to the scalar product defined on your space, okay? Hi. And this scalar product, if you wanted to make the Dirac operator self-adjoint, well, then you needed to make the gamma mu's self-adjoint as well, okay? As well. Sorry. Now, if your manifold is Riemannian, then it's quite easy to do, and the scalar product is just some definite positive inner product on spinors. This is the usual case, okay? But as soon as the signature of your space is not Riemannian, as soon as you have one gamma matrix that squares to -1, then your inner product on spinors cannot be definite positive. In fact, it ends up having a neutral signature, for the simple reason that if your gamma matrix squares to -1, and if it is self-adjoint as well, then the gamma I dagger times the gamma I is -1, and this is impossible if your inner product is definite positive. So you need it to be, you know, indefinite. And this is the reason why we need Quine spaces, spaces with indefinite inner product. So what is a Quine space? First, a Quine space is just a complex vector space, like a Hilbert space, okay? And then you need some indefinite scalar product defined on it, usually non-degenerate. You need to be well-behaving. I will denote Q the quadratic form of the indefinite inner product here, okay? And the simple example is, of course, the complex Minkowski space. You have a minus sign in front of the product, the first two components, and then plus signs. Okay, Quine spaces need to have additional properties. They need to be well-behaving. You need your Quine space to have at least one decomposition into two subspaces that are mutually orthogonal, okay, and such that the quadratic form is definite positive on one of the subspaces and negative definite on the other subspace, okay? Now, once you know that such a decomposition exists, you can put some proper topology on it, but I won't elaborate on that because I simply will not use the topology of the Quine space. And of course, if you have such a decomposition, then you have many possible decompositions, okay, that have the same properties. Okay, so Quine spaces are very interesting, but we do not have many tools on them. When you want to make a computation, it's much easier to use a Hilbert space than a Quine space. So it would be nice if we could put a Hilbert space structure on a Quine space. So you need a definite positive inner product. And the way to do that, the easiest way, is to use the decomposition. You have, for example, two vectors phi and psi in your Quine space. You decompose them into their components. You take the product of the positive components, then you subtract the product of the negative components. This is positive. This will end up being, you know, a definite positive product. This one is definite negative, but with the sign, the total product is definite positive. And this is how you put a Hilbert space structure on your Quine space. Of course, this definite positive inner product depends on the decomposition. Okay, so it's not unique. You have many Hilbert space structures on a Quine space. But what is fundamental, and I insist on this, in our work, what is fundamental is the indefinite inner product, not the definitive positive one. The definite positive inner product is just a tool to simplify the computations, okay? And here's a simple example once again, complex Minkowski space. The definite positive part of your space is just the space, and the definite negative part is, you know, the time direction. And the definite positive inner product is the canonical one, okay? Very simple example. Okay, now it can be pretty complicated to use the decomposition for computations, so we need to simplify it a bit. Here's what happens. You define an operator that we call fundamental symmetry, Actually, it's not that fundamental, but this is how it's called. Which is sort of a gradient for your decomposition. It takes the value +1 on the k plus space and -1 on the k minus space. It has very interesting properties. It squares 1. It is self-adjoint with respect to the indefinite inner product, and I call this Krein self-adjointness to distinguish it from Hilbert self-adjointness. And you can use it to parameterize your decompositions of your Krein space. If you have a gradient, it means you have a decomposition. So if you have J, you have K plus and K minus, and it works also the other way. If you have K plus and K minus, you have J. Okay, and you can write it. You can use it to write in a very simple form the definite positive inner product that corresponds to this decomposition here. See, this formula here can be simply written in this way. So the definite positive inner product that depends on your decomposition is obtained by simply researching the fundamental symmetry between your two vectors. Okay.
Perhaps this is automatic in Krein spaces, but in infinite dimensions, all operators have a joint. It's not like Hilbert modulus.
I'm sorry, I couldn't hear you.
Automatic that all operators have a joint operator in Krein spaces.
Well, it depends on your topology. So I'm just going to assume yes, that indeed all operators have a joint because I don't want to.
Hilbert modulus.
Huh?
It's not like Hilbert modulus.
It's a bit more complicated. Okay. Most of the time I will treat my Krein spaces as if they were finite dimensional because I'm more interested in physics than the math really. And I don't know much about Krein spaces yet. I'm just going to use them. Okay. So for the complex Minkowski space, the corresponding fundamental symmetry to this decomposition is simply this, okay? So you see it takes the value -1 on this space here and value +1 on this space here, okay? Okay, so, you know, this is basically the metric of a Minkowski space-time. Now, you can define the adjoint of an operator with respect to the indefinite inner product. I will denote it with a cross here. It's T cross to distinguish it from T dagger, okay? If you have a fundamental symmetry or a decomposition of your Krein space, then you have a definite positive inner product with respect to which you can define the adjoint of an operator that I will denote T dagger, okay? Because this is the Hilbert adjoint of the operator. And obviously this depends on J, okay? Most of the time when you're making calculations with Krein spaces, you will pick a fundamental symmetry J that makes your computations easier to handle. So you have sort of a preferred fundamental symmetry. So even if T dagger depends on J, we'll just omit the dependence, okay? Okay, now, when you're working with the Hilbert space, you represent your symmetries with unitary operators, okay? For Krein spaces, you need the equivalent of a unitary operator. It's something that needs to preserve the inner product, but this time the indefinite inner product. So you need the operators that satisfy this equation. That's what I call a Krein unitary. For example, if you're trying to represent Lorentz transformation on the complex Minkowski space, well, your Lorentz transformations are maybe not unitary, but they're unitary with respect to the indefinite inner product that you have here, okay? So if you're working, for example, in complex Minkowski space, then your Lorentz transformations are Krein unitary. Okay. So now I'm just presenting the different tools that you have at your disposal when you're working with Krein spaces. And I think it's important to know them and know how to handle them. Okay, now, suppose you have two decompositions of your Krein space, k plus plus k minus, and k plus prime plus k minus prime. Well, they are isomorphic, aren't they? Because the signature of your space is always the same. So both spaces k plus and k plus prime should have the same number of dimensions. Both spaces k minus and k minus prime should have the same number of dimensions. So you can always build a sort of isomorphism between these different components, these different subspaces. Since this is an isomorphism that maps the definite positive part of your space to the positive part, and then a negative subspace to a negative subspace, well, sort of looks like it could preserve the inner product, okay? So maybe That's what we should look for, an isomorphism that preserves the inner product. And in fact, in the finite dimensional case, you can prove that such an operator always exists. Obviously, it preserves the inner product, it's a prime unitary. So you can prove this theorem using Hilbert space techniques. Okay, so you need to pick a fundamental symmetry, and then you make a few computations, you do a new Hilbert space. And what you can prove is that all the fundamental symmetries J can be obtained from one of them by applying the Krein unitaries. So if a Krein unitary can map any fundamental symmetry to any fundamental symmetry, then you can map any decomposition to any decomposition and any Hilbert space structure to any Hilbert space structure, which means that they are all equivalent. Okay, there is no really preferred decomposition or preferred Hilbert space structure. They all behave the same. Again, I insist on this. What is fundamental is the indefinite inner product on your space and the definite positive product you could define. They all behave the same. Which means that if you are going to make a computation, you could always pick one fundamental symmetry and make your computations with it, and the result will always be the same no matter what fundamental symmetry you could have picked. Okay? So you can't choose one. It doesn't matter. Okay. Now, you can do even better than that. You can take a Krein unitary, and then you pick some definite positive inner product, and you do a polar decomposition of your Krein unitary. And you can split it in two parts. The first part, which is the phase part, is both unitary and Krein unitary. And by unitary, I mean Hilbert unitary and Krein unitary as well. Okay. The second part will be Krein unitary and positive self-adjoint with respect to the definite positive product. Okay. And now what happens is that all your fundamental symmetries can be obtained by applying only the positive parts of the Krein unitaries to any fundamental symmetry. Which means that any two decompositions, any two Hilbert space structures, can be related by a Krein unitary operator that is also positive self-adjoint. Okay? And the physical significance of this is the following. Consider, for example, the complex Minkowski space. If your Krein unitary is a real matrix, then it corresponds to a Lorentz transformation. Okay? The unitary part can be shown to correspond to a rotation in space, whereas the positive self-adjoint part is a pure boost, which means that your different Hilbert space structures and different decompositions can be related by pure boosts. Okay? So this has to do basically with covariance. Okay? This was pretty obvious from the complex Minkowski space example in the beginning, where I said that K plus and K minus are space and time. And there is an even more interesting result. This actually works for the representation of the Lorentz group on spinors as well. You can do the same thing with spinors. Okay? So you take a Lorentz transformation represented on spinors, it is Krein unitary, and then any two fundamental symmetries on spinors can be related by a pure boost. Okay.
Excuse me.
Yes.
Just a quick question. You keep using as an example Minkowski complex.
Yes.
Why not real? Because
Well, because the Krein space is complex. So I had to complexify it. I guess it would work.
Why not use the example of spinors in the?
Oh, we did that too, but as an example, I thought it would be simpler to use Minkowski than spinors. But I'm going back to, I'll be talking about spinors as well in a few seconds. I just thought that I would start with Minkowski because it's easier to see. And now spinors. Okay, so consider the Clifford algebra of signature 1, 3. I'm going to apply this whole Krein space thing to spinors now.
Wait, can I follow up on that? So what goes wrong if you take a real Krein space?
Nothing.
Oh, it can be real.
Yeah, it can be real.
Okay.
Totally can be. But, you know, since Hilbert spaces are complex and we're trying to generalize that, spinors are usually complex, so this is why I need a complex space. Okay, so Clifford algebra 1, 3, which means that we have one matrix that squares to minus 1 and three matrices that square to plus 1. This is my convention, okay? Now, you can prove that there is a unique scalar product on spinors that makes all the gamma mu's self-adjoint. This is in a very interesting paper by Robinson that was quite neglected by the mathematical community. You should read it. It's very interesting. It says that there is a unique inner product up to real factor on spinors that makes all your gamma mu's self-adjoint. Now remember what I said at the beginning of the talk. If I want my Dirac to be self-adjoint, I need the gamma mu's to be self-adjoint, which means that the inner product that you need to define on your spinors is practically unique. It's given. That's what makes it so fundamental. Okay? That's why it's so important to start with the indefinite inner product. It's so you can have your Dirac self-adjoint and your gamma mu self-adjoint. Now, here is your chirality operator for your Clifford algebra. It turns out to be Klein anti-self-adjoint and not self-adjoint as in the Riemannian case. Okay? Very interesting difference that we'll come back to later. Now, you need also, for example, a charge conjugation operator. So we pick the anti-linear operator that anti-commutes with the gamma mu's, and it's anti-unitary. It's not always the case, okay? But for this Clifford algebra, you can prove that C cross C is equal to 1. And of course, gamma 5 and C will correspond later to my gradients and real structures, okay? Yes?
So don't people normally have gamma naught squared as plus 1 and the others
I'm sorry?
minus 1?
I couldn't hear you.
Don't people normally have gamma naught squared as plus 1?
Some people do. Yes.
Well, if you look at the Dirac equation in the textbook, that's what you'll see.
Not always. Some people use the opposite convention.
But then you put an I in your equation.
Yes, I did put an I in front of the Dirac operator.
Yeah. So then these are the wrong gamma matrices.
No, not necessarily. Well, you know, in the end, all the conventions end up being equivalent. So it doesn't really matter.
No, it changes the signature.
It changes the signature, it's true. But the physical consequences, well, it doesn't have any physical consequences.
Yeah, you get the wrong propagator.
Not. You'll see why I need this signature, okay? And it doesn't matter if the propagator is wrong as long as the S matrix elements are the same, right?
So the
So
hole's in the wrong place.
maybe we can
You want
talk about this.
gamma 5 to be a projector on the left and right part, which is the one which are split by the gammas.
Yes.
Not everything is. Once you choose your metric, either plus, minus, 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 or minus, plus, 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 then you don't have that much freedom to.
Yes.
I never remember which is which, but every time I have to sit down with a book and do things in a coherent way. So you cannot take away the I from the gamma 5 without.
Oh, of course, yes.
So your Dirac operator is not self-adjoint. It's anti-self-adjoint.
It is self-adjoint.
But it can't be because gamma naught is
Self-adjoint with respect to what?
your inner product. Here.
Actually, it turns out to be. Okay, my Dirac operator is minus I gamma mu and mu, nabla mu, okay? So minus I nabla mu is self-adjoint.
Yeah.
And gamma mu is self-adjoint, so Dirac operator is self-adjoint.
Gamma naught is self-adjoint.
Self-adjoint, with respect to this inner product.
So it's not the usual inner product.
Oh no, it's not the usual one. This is a new one. It's not the canonical one. But I should have written indefinite inner product, I'm sorry.
So normally you take the positive definite one and you put gamma 0 in.
Exactly.
But that's not this.
No, I'm doing the opposite. I'm starting with the indefinite inner product, then I will relate it to the usual one using a fundamental symmetry, which is almost gamma naught. You'll see.
But okay, let's go and see how you
Okay.
express this in a product. So it's not side bar side.
It is.
Okay.
You'll see. It's very subtle.
Speak side bar gamma 5. So.
The Sharman is that the participant leads it to
No, it's okay. We still have time.
No, that's the
Gamma 5 squared is minus 1.
Oh, gamma 5 squared is plus 1 here, but it is anti-self-adjoint with respect to the indefinite inner product. Okay? So that's allowed. Okay, now, here is a possible fundamental symmetry for your indefinite inner product. Okay? So it's gamma 5, gamma naught. There is a difference. You see the gamma 5 pops up. I could have, it is possible to actually get as a fundamental symmetry I gamma naught, but then you use the inner product that makes the gamma mu's anti-self-adjoint, and then you need to remove the I factor from the Dirac operator. So it's all about conventions, but the end result is always the same. Now, with this choice of a fundamental symmetry, your gamma naught is anti-self-adjoint, your gamma i's are self-adjoint, and there are a few compatible representations with this that are used in physics. In fact, all of them are compatible with this. The Dirac representation, the Weyl one, the Majorana one. I'm going to choose the Weyl representation, okay? Okay, now if you choose this representation, what happens is that the positive inner product that you get using the fundamental symmetry ends up being the canonical one, okay? So this is a definite positive inner product, and now you can insert a J in there to come back to the inner product, which ends up being this phi dagger J psi, and this phi dagger J will just be my phi bar, okay? And now remember, J is gamma 5 gamma naught, but could have been I gamma naught. So it's actually kind of the usual choices in physics. Okay, and with this specific representation, you can check indeed that gamma 5 is anti-self-adjoint with respect to the indefinite inner product, self-adjoint with respect to the definite positive inner product, and that the charge conjugation operator is the following: gamma 5, gamma 2, composed with complex conjugation. And you can compute that all of these quantities here. So C is anti-unitary, Krein anti-unitary, squared to minus 1. And of course, these results do not depend on the representation, okay? But if they don't depend on representation, on what do they depend, you know? Well, it turns out they depend only on the number of space and time dimensions of your Clifford algebra. For the general case, for Clifford algebra of signature TS, you can prove the following. An allowed fundamental symmetry is this operator here. It's either the product of all the time gamma matrices or the product of all the space gamma matrices dependent on the parity of T, okay? Now, with this fundamental symmetry, your gamma mu's are either adjoint or self-adjoint, depending on whether they're squared to plus or minus 1. This is what you use usually in physics, so this is a very useful fundamental symmetry if you're making computations with spinors. The chirality operator is either adjoint or self-adjoint, and this depends on T specifically. It does not depend on the signature T minus S, which would correspond for a spectral triple to the KO dimension, okay? As for the charge conjugation, you can prove that, again, C cross C is either plus 1 or minus 1, and this depends on T and S specifically. Okay, so this is how it works for spinors and Clifford algebras, and now you can use this for manifolds. In fact, you can even use this to sort of try and guess what an indefinite spectral triple would look like. So this is what we did. Okay, first a quick reminder of what a usual spectral triple looks like. You have in your algebra, your Hilbert space, an involutive representation, a self-adjoint Dirac operator, anti-unitary structure that commutes to J and squares to epsilon, self-adjoint chirality or gradient that squares to 1, and either commutes or anti-commutes with the real structure depending on the KO dimension. This is only the even case. I'm only interested for even spectral triples. Now, we go to indefinite spectral triples, and this is what happens. Okay, so the algebra is still the algebra, right? Your Hilbert space is replaced with the Krein space. Your representation is still involutive, but this time the image of the adjoint is the Krein adjoint of the image, okay? So this way, if A is equal to A star, then its representation is a self-adjoint operator. You need your Dirac operator to be self-adjoint, but Krein self-adjoint, so D cross is D. Your real structure C commutes with D squares to epsilon, chirality C squares to 1, and either commutes or anti-commutes with the real structure. So you still have a KO dimension for your spectral triple. But now, gamma is not necessarily self-adjoint, because for Clifford algebra, this is not necessarily the case. So now it's either adjoint or self-adjoint, and J cross J, again, is either plus 1 or minus 1, just as for Clifford algebras. And these signs cannot be determined using the KO dimension, because for Clifford algebras, they do not depend only on T minus S. What do you do to determine these signs? Well, the KO dimension may not be necessary, but if you consider your total spectral triple, the one that you will use to define a gauge theory on a manifold, then all the signs can be determined, all of them, and using the fermionic action, okay?
Do you have some analytical conditions here?
Well, probably. For example, the commutator of D with A should be a bounded operator, etc. No. So far, nothing on that. If maybe it should be, but you.
The subtleties is in the self-adjoint Dirac operator.
I'm sorry.
The subtlety
self-adjoint of the Dirac operator,
Yes?
because it's crime self-adjoint here, right?
Yes?
Which is not self-adjoint.
It is prime self-adjoint?
Yeah, so you don't, but it's not self-adjoint with respect to
Yes,
the
it's not.
structure.
Yeah.
And also you don't have complete resolve.
Well, you know, if you want to define that, you need the Hilbert space structure, right?
Which you have, right? Because you have this fundamental symmetry.
But the fundamental symmetry is not fundamental, that's the problem. So you can't, trying to,
Stromer has the condition.
Hmm?
Stromer has this condition where you change D to a sort of, where you conjugate it by J essentially,
yes,
and then you get an operator which is like the Riemannian Dirac operator.
yes, but,
From that you impose conditions.
yes, but that involves picking a fundamental symmetry, right? And that's not covariant, so we're trying to avoid that. The compact resolvent might be useful if you're trying to define the spectral action, but that doesn't even work for, you know, the semi-Riemannian case, right?
Would you agree that there should be some restriction?
Well, probably. There should be a few more conditions. This is only a temporary list of axioms.
Yeah,
The ones that...
there are conditions you can impose, but you don't need them for the fermionic action. So in get
Yeah,
case,
exactly.
it's not relevant.
Well, you don't even know if psi is in the domain of D. For what psi do you write the fermionic action?
Well, sign in the domain of D.
Okay, what is the domain of D?
I mean, it has a dense domain. Yeah.
Oh, so that's a condition, then?
This is a densely defined operator, which is prime self-adjoint.
Differentiable
And
function.
you see that conditionally go.
Well, in the examples, of course, you know what you have to do. I'm just asking if you have some ideas about that.
We're thinking about a few things, but so far nothing definitive, so I won't delve into that too much, okay? I'm only going to need this. That's why these are the axioms that I'm going to talk about, okay? But I agree there should be a few more conditions, of course. This is not enough to define spectral triple. Anyway, what was I saying? Yes. Consider your total spectral triple with your fermionic action, okay? So it's psi, deep psi. This is what I'm assuming it is. I'm not putting a risk structure in there. And I want my fermions to be anti-commuting variables, okay? Because if you have an action that you're going to use it in a path integral, probably, and your fermions need to be anti-commuting variables. Now, you solve the quadrupling problem by using Barrett's conditions. And this is basically equivalent to requiring that psi is an eigenvector of both j and gamma, okay? Now, there is a phase here. As an eigenvalue for j, you can absorb it in the definition of psi. So you can just choose psi so that j psi is psi. And then gamma psi is plus or minus psi. Well, choosing plus or minus is basically a matter of convention for the chirality. So I'm just going to pick plus, and I choose gamma psi equal psi, okay? Now, if this eigenvector exists and is non-vanishing, then you apply j to this first equation, you get that j squared psi is psi, which means that j squared should be 1. You can do the same thing by applying j here and gamma here, and you get that gamma j psi is j gamma psi. J squared cannot be minus 1, so it needs to be plus 1 here, and gamma j cannot be minus j gamma, so it needs to be plus j gamma. Basically, j squared is 1, gamma j is j gamma. Your K dimension is necessarily 0, okay? So we have the signs. We know for a fact that we need this, and if you want your fermionic action to be non-trivial, then you need gamma to be prime anti-self-adjoint, and j to satisfy j cross j is minus 1. Let's see how this works. So, j cross j is plus or minus 1. It's a sign that I'm going to call kappa. Your fermionic action is this. I replace psi with j psi. J commutes with d. So I get this, j psi, g d psi. J d psi, sorry. Now I'm going to use this, okay? Because this operator is anti-unitary or anti-unitary. I'm going to swap psi and d psi, and I get the kappa sign. But then I also get a minus sign because the psi's are anti-commuting variables, okay? And d self-adjoint, so S is basically minus kappa S. And if your action is non-trivial, then you necessarily need to have kappa is minus 1. So, right, so j cross j should be minus 1, and you can do the same computation by replacing psi with gamma psi and using this, you get that gamma cross should be minus gamma, okay? So, if I want my spectral action to be non-trivial, I need to have these signs and these signs as well. So for my total spectral triples, I know all the signs that I need. Now, usually for computations you need a fundamental symmetry, so you pick a fundamental symmetry J. You want to recover the usual properties of J and gamma. So you want, for example, J to be Hilbert anti-unitary, and this is easily achieved by picking a fundamental symmetry that anti-commutes with the real structure. Same thing for gamma. You want your gradient to be self-adjoint, Hilbert self-adjoint, because this is what you usually have for a Riemannian spectral triple. And this can be done by using an odd fundamental symmetry. And you also want your representation to be Hilbert involutive. And this can be done by picking a fundamental symmetry that commutes with the algebra. And this explains all the choices that you can find in the literature when it comes to the fundamental symmetry. People usually choose a J that either commutes or anti-commutes with J, a gamma that either commutes or anti-commutes with J. And this is how we can explain it. Okay, now I have my indefinite spectral triples. So far, so good. You guys are still following, right? Now, I need a spectral triple that corresponds to the standard model. And this is usually done by building the tensor product of two spectral triples, the commutative one, the finite one. So I need a tensor product of spectral triples. And this tensor product will be graded for two reasons. First, thanks to Cohen van den Dungen for the idea. And the second reason is that this is how it works for Clifford algebras. And as I told you, we draw a lot of our ideas from analogies with Clifford algebras, okay? So you have your Klein space. It's graded thanks to the gradient gamma. The algebra is usually even because it commutes with gamma. The Dirac operator is odd. J has a gradient too, which is given by the epsilon second sign, okay? The Karachi operator is even. It's trivially even, okay? It commutes with itself. Your fundamental symmetry, well, if you're going to choose one for computations, then you're probably going to make it, to choose it such that the Karachi operator is self-adjoint. And this means that you can prove that then the gradient of J corresponds to the sign that appears in front of gamma when you compute gamma cross. Okay, so the gradient of your fundamental symmetry corresponds to the self-adjointness or anti-self-adjointness of your Karachi operator. But since the fundamental symmetry is not really fundamental, I won't use it. Most of the time, this gradient will be simply given by gamma cross equal plus or minus gamma. Okay. Okay. So this is how it works. This is how the gradient of your spectral triple works. Now I have two indefinite spectral triples. How do I build the tensor product of the two? Again, Clifford algebras. I'm going to use Clifford algebras to get the rules. All these rules work for Clifford algebras, and I'm going to assume that they work for spectral triples as well. So the algebra is just the tensor product of the two algebras. The Klein space is a tensor product of the two Klein spaces, and the odd and even parts are given by this. This corresponds to the following gradient operator. So the gradient is just the combination of both gradients. The Dirac operator is this. So it's D tensor 1 plus 1, D1 tensor 1 plus 1 tensor D2. So it's just a sort of graded sum. It's a graded combination. Now the real structure. The real structure has quite a bit of an involved expression. It's this one. Okay. So it's not just J1 times J2. You have to put the Karachi operators in there somewhere because you need to compensate for a few signs that appear here and there. And the result is that you get a total spectral triple of k dimension. That is the sum of the k dimensions of your two initial spectral triples. So with this, the k dimension is additive. Okay, it adds up just as for, just like we needed. Okay, now how about the inner product on the Klein space? Am I just going to take the product of the two inner products? No, it's too simple, and it won't work anyway. You have a constraint. You want your Dirac operator to be self-adjoint. Yes. Yes. I'm sorry? I can't hear you. Yes, yes. why not? Since it's the same thing, I'm using graded tensor products. You know, it's the same thing. But since they're both even, you're right. You know. Okay. Okay. So now the inner product. I need an inner product that makes my Dirac operator here self-adjoint. So you can see that this, maybe I should explain why it looks like a Clifford algebra thing. When you're building the tensor product of graded tensor product of two Clifford algebras, if you combine two vectors, v and w, the expression of these, of the sum of the two vectors looks like this. Replace d1 with v and d2 with w, and v plus w will look like this. So this is why it looks like Clifford algebra. So we use this analogy to compute the correct inner product on the total Klein space that makes the D self-adjoint. And it looks like this. So you can see that it is the product of the two inner products, but there is an additional sign that is involved here, the sigma, which depends on the gradient of psi2. Okay, this is a complicated expression. You see that it depends on the gradings of, basically on the self-adjointness of gamma 1 and gamma 2, okay? Yeah, no, it looks horrible. But it works quite well because thanks to this inner product, the Dirac operator is self-adjoint. The Klein adjoint of T1 times T2 is basically given by the Klein adjoint of T1 times the Klein adjoint of T2 plus the cosine sign, okay? So this is nice. And if you pick two fundamental symmetries, J1 and J2, you can combine them to build a fundamental symmetry for a total Klein space. Not that we're going to need it anyway, but here's its expression. So you see it involves a sign, and also it involves the Kirachi operators. You need to put the gradients again in the expression to get the right fundamental symmetry. Okay, this is not very interesting. What's interesting is this. Usually, when you work with spectral triples, you don't do graded tensor products, okay? It's non-graded tensor products. Well, I'm going to relate my graded tensor product to a non-graded tensor product, because non-graded tensor products are easier to handle. I actually do all my computations using non-graded tensor products, whereas my thesis advisors prefer to use the graded version, but the results are the same, so it's nice. Again, Clifford algebras as a rule to deduce these expressions. This is how the graded tensor product works. T1 times T2 acting on psi1 times psi2 is this expression. You don't act naively with the operators on the vectors. You get an additional sign that comes from the fact that psi1 and T2 are swapped when you compute the product, okay? Same thing for the product of operators. And this rule can be obtained by this representation. You take T1 times T2 and you can get a non-graded representation of this operator in the following way. You just put a gradient in front of T1 to the power of the gradient of T2, okay? And here's what happens for your spectral triple. The space, the Klein space, is obviously the tensor product of the Klein spaces. Graded or not, it doesn't matter. The algebra, since they're both even, then you can remove the hat. Your Dirac operator, D1 times 1 remains the same. 1 times D2 becomes gamma 1 times D2 because D2 is odd. Okay, this is the usual result for the Dirac operator. The restructure becomes this. You see, I had a gamma 1 here. I lose it thanks to this gamma 1 here. And this is just J1 times gamma 2 to the order of G1 times G2. If J1 is even, then you get usual result. If J1 is odd, you get an additional gamma 2 factor. And this results, this is what we were expecting because this one in Van Heck's paper on the product of free spectral triples, okay? So we knew what to look for. The gradient is, of course, the combination of the two gradings. And now what about the inner product? Well, your inner product can be written this way, okay? So it's basically the product of two products. The first product on the first spectral triple is the same. And the second product is this. See, here I had the sigma sign, where I'm going to rewrite this. The sigma sign will appear here between phi2 and psi2 as some operator beta. okay, that takes the following values. So we can rewrite it this as the product, I have two products. It's as if you had this inner product here on the second sector triple, okay, if you're working in the non-graded version of the thing. And this beta here is always self-adjoint with respect to the total inner product, the second inner product, sorry. And the fundamental symmetry takes this form, okay? Okay, now this is how you construct a tensor product of spectral triples. We can move on to the standard model. So, you're going to construct a spectral triple that is the product of two spectral triples. The first one is the commutative one, which corresponds to the manifold of signature S and T. And its scale dimension will be S minus T. The gauge part of your spectral triple is a finite part. And this we know is of scale dimension 6. I'm going to use the same finite spectral triple as in Cosmos. Thanks. I think I won't have time for questions. So, you build your tensor product of spectral triples. The KO dimension is additive. So I get the following equation. S minus T plus 6 is basically 0. The manifold is 4-dimensional. So S plus T is 4. And there is only one solution to these equations. And it's TS equal 1, 3. So I have to choose for my manifold the signature minus plus plus plus. Okay? For this to work. And obviously this depends on the conventional Dirac operator. If I had chosen the other convention, I would get the other signature. So, I'm going to review very quickly the spectral triples involved. You have the commutative spectral triple with the algebra of smooth functions. The Klein space is some proper completion of smooth spinors. I'm going to use smooth spinors everywhere, anywhere, so I won't bother much with that. The indefinite inner product, that I have to determine yet. The Dirac operator is this, minus I gamma mu nebula mu. Now the chirality is the gamma 5, and it is Klein anti-self-adjoint, okay? And the restructure is the charge conjugation that anti-commutes with gamma mu's.
But your M is even just R4. Or
Right?
M
Sorry?
is just R4 for you.
It doesn't have to be, but sure, why not?
Oh, but so the gamma 5s and so on, I mean, these are the local expressions?
It's a local expression. Locally, it will look like gamma 5. Of course, if you have a complicated spinor bundle, then... Let's just assume that it's...
Point.
Huh?
But okay, never mind.
I'm sorry?
That's the point.
Okay, so your algebra is the usual one. The Klein space is 96-dimensional, so you have all these crazy fermions everywhere. This is how I'm going to write my matrices. This is the representation that I use, okay? I start with right particles, then left particles, anti-right particles, anti-left particles. I start with leptons, then I move on to quarks. And there are 3 generations, of course. The indefinite inner product. I don't know what it is yet, but I know I can write it in this form, okay? It's U dagger times some self-adjoint matrix times V. And all I have to do now is determine this H matrix, okay? The Dirac operator, I need to determine it yet. Chirality and restructure, well, it's the usual ones, okay? Now, the total spectral triple. I'll just use my rules, okay? Tensor product, tensor product. I'm writing this in the non-graded form because this is easier to recognize and understand. The indefinite inner product is the product of this commutative product times this finite product with the H and the beta as well, okay? The Dirac operator is the following, chirality is this, and now restructure. You see, if you compare it to the Riemannian case, you see that you have a gamma F here, okay? And this gamma F is very important. Well, by the way, I forgot to tell you that my right particles have chirality -1 and the left ones have +1, okay? This is my convention. You could start with the following hypothesis. You could assume that the finite part is Riemannian, which means that H is basically the identity, okay? Because this is what you usually have. But then, because gamma F is Klein self-adjoint, as gamma M is anti-self-adjoint, the beta matrix that I will insert in my indefinite inner product is gamma F. So, this product here is phi F, gamma F, psi F. And if you use this to compute the fermionic action, you get the wrong result. In the kinetic term, for example, you get opposite signs for the kinetic energy of left and right particles, and that's not right. It can't be like that. So we had to try a few other choices, and the simplest one that works so far is the following. this matrix H, which has as a value, it takes the value -1 on right particles and the antiparticles, and +1 on the left particles and the antiparticles. Okay. This is H, so I know my inner product on the finite part. Gamma F with this choice, once again, is Klein self-adjoint, so I know which beta operator to pick, and it's going to be gamma F. So in the F beta product, I have to multiply H by gamma F, and I get this. I get this matrix, which takes value +1 on particles and -1 antiparticles, and this happens to coincide with van den Lundgren's choice for the product on the finite part. So this is, yeah, it's practically the same result. Probably for the same reasons. Now, you can also check that J cross J is -1 and gamma cross is minus gamma, so everything works. Your spectral triple will not be trivial, okay? Your fermionic action will not vanish, hopefully. Fingers crossed. Okay, let's compute the finite Dirac operator. It needs to commute with J, anti-commute with gamma. It needs to be self-adjoint, but self-adjoint with respect to the product on the finite part that involves the H, okay? This is important to remember. And it takes this form. Now, usually, you have here X and here X dagger, for example, but this is not exactly Hilbert self-adjoint. This is not the usual self-adjointness. So you would get here X and here minus X dagger, but I don't like having minus signs. I wanted both matrices to have the same factor, hence the minus I factor here and the plus I here. And these I factors will actually drop out of the fermionic action later. The matrices Y and Z need to be symmetric, okay? Now, this is the part where you have to apply the order 1, 0, 1, 2 conditions. The order 0 condition is easy to check. The order 2, 1 and 2 conditions will constrain your Dirac operator. I'm using the previous form of the order 1 and 2 conditions because, well, we did not have enough time to use the new version for obvious reasons. So this is the order 1, 2 conditions. Here J2 is the order 2 junk, okay? What changes is that the opposite of an operator is not J A dagger J minus 1, now it's J A cross J minus 1. If you don't replace it with a cross, well, two things happen. First, it doesn't work for the commutative spectral triple. And the second thing that happens is that obviously your formalism is not very covariant, and that's bad. Now, what solutions are allowed by these equations? The Z matrix vanishes. The Y matrix almost vanishes with the exception of this small A term here that will couple the right neutrino to its antiparticle. So it's a majority mass term. The X matrix, well, you see here, these zeros here are imposed by the equations. These blue zeros here, these are the ones we had to cancel by hand to recover the standard model. But actually, they're allowed to be non-vanishing by these equations. Maybe we'll find a way to make them vanish using Latham and Shane's new version. Anyway, this gives you the usual finite Dirac operator that you have in the non-commutative standard model, with the exception of these I factors here. Now I'm going to tell you why the I factors drop out. Okay, you fluctuate your Dirac operator using the usual formulas. You get the gauge terms, you get the Higgs terms. The B mu, the gauge field, is the usual one, okay? It has the same exact expression as in the Riemannian case. The Higgs field, it takes this form. You replace the matrix X with its fluctuated version. This is basically the Yukawa couplings of the Higgs field with usual fermions. What changes is, again, the I and minus I factors, okay? Okay, now you can compute the fermionic action, but first, you apply Barrett's conditions. So you take a generic vector in your Klein space. You split it in 4 parts. You have all the spinors for the right particles, the spinors for the left particles, etc., etc. And you apply the Barrett condition, then the spinors for the anti-right particles is basically the spinors for the antiparticles, but with charge conjugation applied to them. Same thing for left particles. And now you see why I have this I factor here, okay? If I did not have this imaginary factor in front of psi L, I would get a minus sign here, and then I would not be able to combine the left and right spinors to form a particle spinor. Same thing for antiparticles. And these spinors for particles and antiparticles would not be easily related by the following formula. This is what you have in physics. If you want this, you need this I factor here. And this I factor is exactly what's going to compensate the I factors here. And everything drops out of the fermionic action. You can compute it. The kinetic term is basically 2 times the kinetic energy of the particles, because the antiparticles give you the same contribution. And this is a particular example of why you need to choose J cross J equals -1. If you choose J cross J equals +1, then the antiparticles give you the opposite contribution to the particles, and you get 0 here. But if J cross J is -1, they both give the same thing, and your kinetic energy is twice the kinetic energy of the particles. Same thing for gauge terms. The coupling to get the gauge fields is twice the coupling of the particles with gauge fields. As for the mass terms, it's the same thing. So this is basically the couplings of electron particles through the Higgs, plus the Majorana mass term for the right neutrino, where I can choose A to be real by absorbing its phase, basically in the neutrino spinor, the right neutrino spinor. So far, I have the exact fermionic action of the standard model using this spectral triple, okay? So this kind of confirms that the spectral triple is the right one for the standard model on a Lorentzian manifold. But I only have the fermionic action, of course. I need the bosonic one too. I won't elaborate much on the bosonic action, but I'll tell you a proposal to get the bosonic action. In the Riemannian case, you use the spectral action because you have a Hilbert space, and this is well defined and converges. Now, this action has a very interesting property. It's invariant by the action of the unitaries of your Hilbert space on the Dirac operator. Now, you could do the opposite and start with this invariance as a basis for defining the action, because it turns out that for Hilbert spaces, at least in the finite dimensional case, any expression invariant by the action of the unitaries is of this form. It's a trace of something, okay, or a function of traces. So you could take this invariance as a basis for defining the action, which will not be spectral anymore, but will be bosonic. So here's a proposal. You have to choose the most general functional of the Dirac operator that is invariant by the action of symmetries, where the symmetries are not unitaries anymore. They're Krein unitaries, okay? I won't tell you more about it because this is still work in progress, but here's our proposal for bosonic action. And now I can conclude by summarizing. What do we have? Well, today we saw a proposal for axioms for indefinite spectral triples. We saw that Krein spaces are necessary and how they can be used to define indefinite spectral triples. We saw how you can recover the standard model of particle physics. Well, almost, because we have the fermionic action. We don't have the bosonic action yet. And maybe we can define two symmetries. Who knows? Thank you for your attention. This is okay. Took too much time. Yes.
I don't know if you're not ready to talk about this yet. I don't know. There's something that Christian mentioned outside the elevator the other day was that if you take things to be invariant with respect to these unitaries, you get some of the extra constraints between what would naively be regarded in effective field theory as different coefficients in the action.
Yes.
But similar to what you get from the spectral action. Is that? So in other words, the spectral action gives you some extra constraints between coefficients in the action.
Yes. Yeah.
And
It does actually.
Those can be seen as following from the extra unitaries, which are not shifts.
Yes. You can check this on a few interesting examples. You can use a finite number of unitaries to, for example, relate all the couplings of the gauge fields, the G1, G2, G3. You need only a finite number of unitaries to actually show that they obey the grand unification relation. Okay, the grand unification equation. Just by requiring that the action should be invariant with respect to these unitaries. You actually only need 5. Very neat result.
And the relationship between the Higgs cortex off-coupling and
You get relations for these two, yeah. That's what we've done so far. Other questions? Yes?
Ecological question. Can you define your junk explicitly?
Here?
What is this? I mean, we have complete operators for getting whatever, I mean, whatever was your convention. These are complete operators, so that's just in your case, the operators of what kind?
I'm sorry, hold on.
J2, what is
J2 is the order 2 component of the junk, and the junk
yes, what is the jump? How do we define that?
is basically the hold on.
What are these guys?
Huh?
What are these guys?
I'm sorry,
What is this jump? Yes, yes.
the junk. So usually what we do, you can, for example, have your algebra A, okay, and then you define the universal differential algebra.
Okay, complete operators A, complete operator D. This step, can you say what is J2?
I'm sorry, I'm not sure I understand your question.
Yeah, the concrete operator.
We have complete D, we have complete A.
For the standard model, what is
Oh, you want its exact form? Oh, damn it. That's a hard question. Oula. Sorry. It's way too complicated. It looks, the junk looks pretty ugly. In fact, to solve the equation, we did not determine the junk exactly. We determined a subspace to which the J2 belongs. And this subspace is it looks kind of horrible. You can take a look at our paper to understand what it looks like, because there are too many matrix elements because the Dirac operator is too big. So you have many non-vanishing elements. And now you're probably asking me this because you want to know how I solve this equation, right? Yes. Well, something interesting happens. All the non-vanishing elements of this anti-commutator correspond to vanishing elements in J2. So basically what it tells you is that, okay, I need to write this. For example, your anti-commutator will have non-vanishing matrix elements here, whereas the junk will have non-vanishing matrix elements here. So you see that if this matrix operator is in this vector space, then it simply needs to vanish. Okay? So the equation is basically anti-commutator equals 0. It simplifies to this.
Shane?
Oh, just while you're on this side, so I didn't hear what you said. These capital A's just above the allowed solution, are they zero forms or are they any
Here?
forms? Yeah.
Or it could be anything.
Any-
Yeah. There might be a sign involved here, plus or minus sign, but it's not important for the
So
equations.
up to
So
a sign.
yeah, I just dropped it.